In this problem, we are told that a tiny hole develops in the wall of a rigid tank whose volume is 0.7 meters cubed, and air from the surroundings at 1 bar 25 degrees Celsius leaks in. Eventually, the pressure in the tank reaches 1 bar, and the process occurs slowly so that the heat transfer between the tank and the surroundings keeps the temperature of the air inside the tank constant at 25 degrees C. We want to determine the amount of heat transfer in kilojoules if initially our tank is evacuated, and then again if our tank initially contains air at 0.7 bar and 25 degrees Celsius. And we want to ignore kinetic and potential effects in this problem. Now, I'm using a new pen and tablet, so this actually has a screen on it, so we'll see how this works out. First, let's define our control volume. So our control volume is going to be this tank, and what's happening in this tank is that we have a hole that develops. So we have a hole, and all of a sudden we have air that is gushing in. So let's start with our mass balance equation. So the change in mass over time, and this is of my control volume, is going to be equal to the sum of my mass flow rates that are going in and subtract the sum of my mass flow rates that are leaving. Now, we only have air that's going into our control volume. We don't have anything that's leaving, so our exit is going to go to 0. And we only have one hole, so we only have one inlet. So this, the farthest we can simplify this right now, is the change in mass of my control volume, dm dt, is going to be equal to, we'll just say mi, my mass flow rate that's going in. Okay, let's move on to my energy equation. My energy equation says the change in energy with respect to time is equal to the rate of change of my heat minus the rate of change of work, and these are of my control volume. Then I'm going to add in my inlet, my mass flow rate of anything that's entering, times the enthalpy plus my kinetic energy effects plus my potential energy effects, and subtract out anything that's leaving my system. So again, this is going to be enthalpy, and then this is going to be my kinetic energy effects, and then this is going to be my potential energy effects. Now let's simplify this a little bit. In this problem, we have no work. There's no paddle wheel, there's no anything. So this is going to go to 0. We have no exit, so this entire term right here is going to go to 0. We can ignore our potential energy effects, and we can ignore our kinetic and potential energy effects. So there's one more simplification. By ignoring kinetic and potential effects, this term right here, we know that my total energy is equal to kinetic energy plus potential energy plus internal energy. So if we had looked at the difference of all of these, kinetic energy and potential energy are going to go to 0. So all we'll have here is the change in my internal energy with respect to time is equal to the rate of change of my heat transfer plus the mass flow rate of my inlet times my enthalpy HI. Okay, so now what can we do? Well, we can link these together. We can substitute the equation right here. So what I'll have is du, and this is capital U. So I'll try to denote that with that. So du dt is equal to q dot plus dm dt times enthalpy. And what I want to do is I want to take the integral of all of these terms. Well, there's one thing I need to know. What's going on with enthalpy? A really important word to look for is, well, the process occurs slowly. Because the process occurs slowly, this means that the air leaking in always is at 1 bar 25 degrees Celsius. The most important part is this 25 degrees Celsius. So what this means is that the enthalpy is constant. So you're looking for that in these type of problems. It's an idealization that we make. It makes the problem a lot easier because now when we take this integral, h can come outside of the integral. When we do that, we're going to have some change in, I'm going to write it like this first, some change in my internal energy is equal to, well, Q dot is just going to become Q, heat transfer. Then here, this is going to be some change in mass. And because enthalpy came outside of our integral, it's just going to be times our initial enthalpy, or enthalpy that's coming into our system. We also know that enthalpy is equal to our internal energy plus P V. So we can make that, let's make that substitution. And at the same time, let's look at think about what our change in internal energy is. Our change in internal energy is going to be some mass at time t times my internal energy, this is lowercase u, at time t, right? My mass is going to be changing and my internal energy is going to be changing. Then we'll subtract out my mass at time 0, the initial mass, times my internal energy at time 0. This is equal to Q. And then we're going to do the same thing here. We're going to have a couple of substitutions. So first we're going to say plus my mass at time t minus my mass at time 0. And we're going to just surround this by a bracket. And then we're going to multiply by U plus PV. Now we do a little bit of algebra. Actually, there's one more sort of thermodynamic thing we can do. Because we're dealing with air, we're going to assume it's an ideal gas. Right? Yeah, air. So because it's an ideal gas, we have this equation that PV is equal to RT. So what that means is we can substitute for PV, we can just put RT right here. All right, so now let's go through and let's multiply some stuff across. Watch out where my head is. But we're going to have MT UT minus M0 U of 0 is equal to Q. Multiply this, so we get plus M at time t times, we do need to be a little bit careful. This, I was a little sloppy, but this is my initial internal energy. This is my initial temperature. So I do have subscripts of I on those. So then this is going to be times U of I, and then plus M, my final mass, times R of Ti. Now we're going to subtract M, my initial mass times my initial internal energy minus my initial mass at time 0 times RTI. And that all fits. Cool. Okay, so now let's just simplify this a little bit more. And I'm going to bring everything to one side of the equation and solve for Q. So I'm going to put it over here. So I'll have Q is equal to M T U T minus M0 U0. So then minus MT UI plus mt r ti. I think we'll be able to fit this all. Actually, that's a minus, right? Yeah, that's a minus. And then the other two terms are plus, so plus m of 0 times u of I plus m of t times r ti. Now, what I'm going to do is I'm going to group all my like masses. So m of t is going to be multiplied by u of t. That's this one. Then minus u of I. That's this one. Then minus r t of I. Okay. And then we're going to take out, so that's this one. Then we're going to take out a plus my initial mass at time 0 times u of time 0. And we have a negative right here. Negative u of time 0 plus u of I plus r of ti. Okay, and this is really going to be my baseline equation. So from this equation, there's actually one more simplification I can make. And this requires understanding what's going on with the ideal gas. Because we're dealing with an ideal gas, we know that my internal energy, U, is only a function of temperature, the property of an ideal gas. So because it's only a property of temperature, my temperature is never changing. It's at 25 degrees C. It's at 25 degrees C, and it keeps it constant at 25 degrees C. So my final temperature, so it's like T2, is equal to T1, which is equal to Ti, all of those, or T0. But my temperature is never changing. So that means my internal energy is never changing. So this internal energy and this internal energy are the same. This internal energy and this internal energy are the same, and they're also being subtracted from each other, right? Because I have a minus sign that I sort of forgot out here. So these go to 0. So now I can rewrite this equation. So this is mass of time t times minus r of t plus mass at times 0 times r times my temperature. So this is the equation I actually want to go with. Now for part A, actually, let me do blue since A is in blue. So for part A, when we do this, well, we're started that my tank is evacuated. That means my mass of my tank is initially 0. And that means this entire part of the equation is just going to go away. So here I'll have Q is equal to mass at time t times minus r t. And this is a t of I, but we know all of my t's are the same. All of my temperatures are the same. But we don't know what my mass is. But what we can do is go back to what's happening with an ideal gas. So with an ideal gas, we know that one equation we have is PV is equal to mRT. So this is going to be valid for my mass at some time. So if I solve for my mass at some time, this is going to be equal to PV over RT. So if I substitute that here, I'll get that this is equal to PV over RT times minus RT. And again, remember, all my temperatures are the same. So these are going to cancel out. And then this is going to be equal to minus PV So my pressure is 1 bar. My volume, it's a rigid tank, means my volume doesn't change. So it's going to be 0.5 meters cubed. And then I just need to do a conversion for bar. So 1 bar is going to be 10 to the 5th Pascal or Newton meter squared. And then I can say 1 kilojoule is 10 to the 3rd Newton meters. And what will happen here? There it is. So when I do that, I'll get 0.75 times 100, and it's negative. So I get this is equal to negative 75 kilojoules. Let's make a better box there. Okay. Minus 75 kilojoules. Okay. Let me get rid of this right here. Now we want to do part B. So when I do part B, it's the same thing, except I can't make this, my tank initially contains air at 0.7 bar, 25 degrees C. So that means my mass is not going to be 0. So when I have this equation, mt of minus RT, that simplifies the same way. So we know that already simplifies to PV over RT times minus RT. So this is going to be minus PV, all right, this is Q, is equal to minus PV. And then we have this part of the equation. So plus my initial mass, M0, times, what do we have? We have RT. Well, we're going to use the same relationship. So PV equals MRT. Now instead of at time t, we'll just have, like, this is my initial. So I'll have M of 0 is going to be equal to PV over RT. All right, so this would be right initial and all my initial values, which would be given from right here. So when we put that into the equation, we'll have this is plus PIVI over RTI, RT, and that's I. And those are going to cancel. So now we're going to have plus PIVI. Okay. So what we'll have is we'll have Q is equal to minus, well, 1. Yeah. Minus 1 bar times 0.75, then plus P, so 0.7 times, again, 0.75. It's a rigid, and this is meters cubed, and this is bar, a rigid tank. We do the same conversion over here. I'm just running out of room. So we're going to have the same conversion. And then what we can do is we can put this in the calculator. So minus 0.75 plus 0.7 times 0.75. Then we multiply by 100. So here we'll get that Q, a little more room, Q is going to be equal to minus 22.5 kilojoules. So that's the difference. So the only difference working this problem is what you do with this term right here, because initially it's evacuated, so it goes to 0. And then when it contains air, you have to work through the ideal gas.